these exams. I remember you always take about 6 of them. You're the exam collector, right? Okay, everyone's here today.
No, everybody.
Not everybody. Okay, let's see which ones are you going to be collecting today? It's not this one. Let's see her. Let's see Wu. Let's see Wu. Sen Bing. Okay, this is he's not in here yet. But she's distance. I believe I have 2 E's, LIU. Chin. It's a what that was she? Oh, recognize her. She's not in here. See, it's not in here. Okay. So what you got yours and say again?
Last name is
Oh, okay. So, last name?
Yes.
Say again? What's your last name? Oh, okay. This one?
Yeah.
Okay. All right. Making progress.
Your normal seat.
Okay. Come on up and grab an exam, even if you don't want to.
I do want to.
There you go.
All right, thank you.
All right.
All right. Let's get this started.
All right, I think today the first order of business should be to talk a little bit about the exams. It's kind of a rush to get them back because I think there was some confusion, or maybe some of these problems seem to be a little trickier than I had hoped, and I think people kind of got the wrong idea. So I'd like to spend some part of today's class going over these because I want to make sure that nobody misses the same problem again on the final. Because some of these problems are so fundamental to the course that you're going to see them again. And it'd be really nice if everybody just, aced the upcoming problem that they learned how to do on exam number 2. So I think I'd like to cover that. Today's office hours as well. So if you have any questions about the exam after class, definitely talk to me. Send me an email because we've got only a few classes left before the final. I've posted the answer key to the exam 2, and I'm also going to go over several of the problems today just so we can make sure that we're all on the same page. So with that, let's see, we're at the PC, right. Let's talk about problem 1, because that one seemed to be a little tougher than I would have hoped. So let's see if we can make this big enough everyone can see at home. Okay, for problem 1, the inspiration for this problem was the decimation in time DFT material that we spent quite a bit of time on going into in detail. And so this problem was hopefully an extension of that knowledge that hopefully you gain from studying the decimation in time DFT. So let's kind of go through it step by step. So we're going to say xk is an endpoint sequence, an endpoint DFT. That's the key part, endpoint DFT of the sequence x of n. Now we're going to define a 2 endpoint sequence, so it's twice as long as the x of n sequence, and we'll call that y of n. Now y of n is kind of a funny sequence. Every other sample is 0, and every other sample is one of the values of x of n. Now, if you've been studying the chapter 4 material, you immediately think, oh, that's just upsampled by 2 version of x of n, which, yes, it is. And you'll see that we get the right answer that we should get when we upsample a sequence by 2 as we go through this. So part A was express the 2 endpoint DFT of y of n in terms of x of k. So let's see how we would do that. If I can get it on screen here. Down here.
So I think
Yes.
I might have misunderstood, like, actually when I was reading it. But so the x n over 2 is the shoot-point DFT, or is the equation we use when doing the 2-point. Two-point sequence, I guess?
Yeah,
So
the DFT of y of n is a 2 endpoint sequence because y of n is a 2 endpoint sequence.
oh, okay.
Now, I guess we could have been really confusing by asking you for the n over 2 point length sequence of y of n or some other crazy, I don't know, barely imaginable what you'd use that for type sequence. But I tried to make it semi-useful. Because this, if you did this right and understood it, then it's like, aha, that's the stuff that we did in chapter 4, where we did it in continuous time there and things were more picture. Now this is, you know, the brute mathematics, the brute arithmetic of the sequence just coming right out. So let's see how that develops here. So this is going to be problem 1, part A. And I think we've already got what y of n is, but we'll write it down one more time. And so it's x of n over 2 when n is even, and 0 when n is odd. Which is good because we have to have something, because when n is odd, then the index into x is a fraction, which is gibberish, right? So we'd have to account for that somehow. So one way to think about this, because it is a little bit slippery, is what is y of n? So you could say that, well, y of n is just a sequence, right? It has these values. It goes on. Let's do one more. There's a sequence of values. That's what y is. But what is it in terms of x? Well, when it's the 0th one, it's x is 0 because that's an even. When it's an odd, it's 0. When it's an even, it's x of 2 over 2, which is 1, and etc. So you really see that y of n is just a sneaky way to say upsample x of n by 2. And our objective is to use the DFT formulas and expressions and manipulate them so we can actually come to that same conclusion that we basically did in chapter 4. This is 2 pi nk over cap n. We'll try to write out the k's here because that's part of the problem. So y of k is a 2n point DFT. So we have all of that going. Now one way I like to attack this to kind of keep myself from getting bogged down too early in indexing adventures is to say, well, before I get lost in the details, I'm just going to reorder this, and I'm going to sum over n even y of n. So n's an even number. And that should be 2n, shouldn't it? I think I already demonstrated the care we have to take. There it is, 2n point DFT. So I'm going to break it into two summations. One is even, and the other one is just the odd stuff. N is odd. And k goes up to 2n minus 1 because it's a 2n point DFT. Okay, now it's time to start sweating the details. I want n to be even. What's the easiest way to do that? I think the easiest, most straightforward way is to think back to that decimation in time, very first step of the derivation, where we say, okay, if you remember in that one, we summed from n equals 0 to, okay, I guess it was n over 2 minus 1. So in this case, n's going to go from 0 to n minus 1, because we're just taking the even values, because n isn't that type of sequence, but it's the even part, right? So I'm just going to make n be an even number, 0, 2, 4, and I'm breaking it into the even and the odd, because why? We know the odds are 0, so I can just willy-nilly eliminate that second term. So I put in a 2 in there, minus j 2 pi, the crucial 2n, divided by 2n. And then we can say, oh, plus these n odds, which is 0 times e to the minus j 2 pi nk over 2n. So I'm just going to start forgetting about that part right now. And of course, k. 2n minus 1. Alright, let's get it all lined up here. So next step, we have to remember y of n equals x of n over 2 for n even. So for all these indexes here, they're always going to be even because I forced it to be even by multiplying it times 2, and n is an integer. So that, I hope, makes it clear that I can replace every single one of these y of 2n's with x of n. Whoops, and so we have x of n there. And we still are left with our e to the minus j 2 pi 2n k all over cap 2n. And k is still doing the same thing. Now the next step of this is to kind of recognize that what the DFT for an endpoint DFT kernel looks like and say, well, what if I were to cancel those 2's, what would happen? So this 2 and this 2, since the numerator and denominator can obviously go away and we can simplify it. Two pi n k all over cap n. 2 dot 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 2n minus 1. So far, so good. Now the key part of this is to recognize that, what is that? That is just an endpoint DFT that we know and love from the beginning of the chapter. So this is an endpoint DFT of x of n. But y of k is a 2 endpoint DFT. So how do we interpret that? And that's where we go back to the way we've interpreted some of these other DFTs for the decimation in time. We interpreted it as modulo n, right? So y of k is going to be, oops, I think I'll make this k, but it's modulo n for k up to 2n minus 1. And so what does that really do? That means for every k greater than n minus 1, we're going to have to subtract n from it and get back to 0 through n minus 1, right? So what's that going to do? As you run through the values, it's just going to make it copy itself all over again. And hopefully that's not too alarming, because if we remember back to sort of our first principles, remember when we were talking about I'm using the right terminology here. When we upsampled something by L, what was the expanded version, or this upsampled or expanded version? It was basically the original version with this factor of L, right? And remember what that ended up doing is usually when we ended up with, let's say, something that looked like this. You know, some kind of, we can make this, pretend it's pi over 2, just for the sake of argument. When we went to the x expanded of ej omega, it basically forced the I guess the frequency scaling kind of adds multiple copies, right? So now if we upsample by 2, let's let L equal 2, what do we end up with? Like pi over 4 minus pi over 4. And then we had copies, instead of at 2 pi, we had copies at pi minus pi dot dot dot. And so this is just basically the continuous stuff that we were wrestling with in chapter 4, making copies. And now it comes back to us with the modulo arithmetic in this example. So I was hoping that people could get down to writing here, and maybe this is a tricky step. I mean, we did it for the decimation in time, but very few people even, very few people even got down to here. And so I wanted to go through this sort of step by step so you kind of see the steps of that, and be aware that there could be a problem, a repeat type problem on the final exam. So you get another chance possibly to repair that. Let's just do part B since we're on this problem. Let's go back to the PC. So part B was, given this sequence and we take the DFT, we get x of k. What is x of n? What kind of sequence is that? Now there's probably multiple ways to work this problem. The way I was hoping people worked it, and I don't think anybody worked it this way, though plenty of people got this problem, got most credit or full credit. I was hoping that people would look at the summary properties of the DFT and think that, well, if I have a sequence and x of n is real, if it's an even, I guess we can just look at it, doesn't really matter. An even sequence gives you the real part of x of k, and then the odd part of a sequence, so XEP, remember, was like sort of the even part of the conjugate symmetric. XOP was sort of the odd part. And you could get those from x of n. Well, imagine you had an x of n that was peculiar. It was an x of n that was fabricated or circumstantially set up, or even contrived, like in this problem, so that XOP was basically 0. So there is no part of the Fourier transform that's going to be imaginary. So this J imaginary part goes away because there is no XOP to take. So the Fourier transform of 0 is still 0. But that's not the only way to do it. In fact, everyone who looked at this, in fact, did it a different way. So let's go back. You can just take a look at the sequence and do our show that it is, in fact, even. And so many people did that. They went and showed that if we take x of n, and I guess I'll just write down what most people did, but a lot of people did the good old table, or basically wrote down this for part B. They said xn is even, and then show the table because x of negative n4 equals x of n, or x of k is pure, and the way I was thinking is x of n is even because x of k is purely real. Either explanation works. Let's go to part C. I think this one might have been confusing to folks a little bit, just because of the way the question is framed. Okay, if y of k is shown as below, so we've got some sequence y of k, sketch y of n using the information in part B, and explain your answer. So we got y of k, we want to know what's going on with y of n. And then we have this information in part B. Well, what am I getting at with information in part B? Well, if we go back to part B, we have some relationship between x of n and x of k is the DFT, and we see x of k is this. Well, if you look at x of k, you see that it is similar to y of k. X of k has 10, a bunch of minus 2's. Y of k has 10, 2, minus 2, 2. So there seems to be some sort of something going on there. So what I was hoping that people would do would say to themselves, okay, if we've got that, let's just kind of write down what we know. So in our back pocket, we have this relationship of xk. That was given in part B. So that was the part B, use this information. So what we want to know is, or at least I was hoping you'd think, is to find y of n. The question is, how does y of k relate to x of k? Because x of k has been given to us. We know what that is. We know what x of n. There's no mystery there. but how does y of k relate to x of k? So once we know this mystery relationship, how do I go from y of k to x of k? Once I know that, well, then I know how to go from, I guess, x of n to y of n, is found. So that was kind of the, I guess, the sequence of steps. So we know x of n relates to x of k. To find y of n, how does y of k relate to x of k? If we can figure that out, we can get from x of n to y of n. So those are kind of the steps. So I was hoping that by looking at our two sequences here, so let's just put them together. We've got x of k is 10 followed by a bunch of minus 2's, right? Minus 2, minus 2, minus 2. And y of k is the same thing. 2 minus 2, 2. So I was hoping that people would say, well, how are those related? Well, the first thing we could do is say, well, I'm not really sure how they're related. Beats me. Let me go see different ways things can relate to each other, right? So if we go to the properties list, we'd want to start looking through different ways for things to relate to other things. And they're off by a sign, right? And that's kind of all we've got to work with here is a -1, right? So if we go through our list of how one thing can relate to another, well, this is x of n. There's an n, but I don't know about n. N might not be negative. N's usually a positive number saying the point of the DFT. So, well, here's property 5. A shifted version of this multiplies x of k by this thing. That's e to the minus j 2 pi then km over cap n. So I guess that could be played with, but let's keep going. You can multiply this times the same thing and shift that, but x of k isn't a shifted version. Yes? Oh, sorry about that. Thanks for that. Sorry. Oh, I guess what I was trying to show is if you go to this summary of properties, we can kind of look through the list and try to find, like property 4, here are two things that are related, but it's off by n, which is obviously positive because it's the length of the DFT. So it's not a negative length DFT. That'd be a different class. Property 5. I'm not sure what this is. It's a shifted version here times this complex quantity here, but you could force that to be -1 because it's e to the minus j pi blah blah blah. You can fill in the blanks. This version, number 6, you can multiply this and get that, but x of k isn't really a shifted version of y of k. It has that weird -1 problem, right? So if you look through here, hopefully this stuff's starting to get complicated here. I hope you might say, well, I'm running out of time. Maybe I'll just try property 5. So what I want to do is see if I can make this complex WNKM times x of k do something for me. So that's what we're going to look at first. Can we get anywhere with that? So if we look at property 5, we say, aha, if I shift the input sequence by some amount we'll call small m, what does that end up doing? It ends up modulating the DFT. But when we looked at our original thing here, 10 is the same as 10, minus 2 is the sign flipped of 2, this minus 2 is the same, and this minus 2 is flipped. So at best it's -1 plus 1 -1 plus 1. And so can we even make it look like that? Right, e to the minus j 2 pi k m all over n times xk. We know what we want. We'd like the sign to flip every other one, and the question is, can it be done? So if I make this e to the minus j, pull this down, this is what? 2 pi mk, and n is given to me as 4 in our example. This is what we end up with. So if we end up with what? E to the minus j, that 2 cancels with that, and so we get pi m over 2 times k. And so I'm hoping that you might say, well, if m was equal to 2, that would go away. And so then we end up with e to the minus j pi k, which might be another way of writing e minus 1k, minus 1 to the kth power. So if we feed that back in, letting m equal 2, then we've got, what, x of n minus 2 must be a DFT pair with y of k. So that puts us back to what is x of n. We knew x of k was modulated x of n, so we just need to go write down what was x of n again, if I can find it. Let's see, page up. Right, so x of n was this sequence. And that's 1 followed by 3 3s. 3 3 3. Let's go back to our chart here. So I just need to shift this in minus 2. So how do we do that? Remember, this is like a periodic kind of shift or a circular shift, and so one of the easiest ways to do it is you can either make that table, or if you've done that table so many times now, you have an intuitive sense for what happens. You don't have to do that anymore, and you can just shift the entire sequence ahead and feed the others back. So this one skips ahead 1 2, so 2, there's 1, and then the 3's continue to wrap around, right? That 3 shifts 1 2 to the end, and then the ones that are here shift around, right? So you end up just sort of shifting it on a tank tread almost all the way around. And so this was the y of n that we wanted to find. All right. I think we're going to skip problem 2. Most people, if they had a problem with that, it was just involving signs, like lost a minus sign or something along the way. I guess one of the weights was what ended up being 0, and that confused people. But I put it in the answer key, and it's fairly straightforward. Maybe I'll put it on screen just for a second. This was part B, and if we go to, let's see what the problem was. A and B. I think the problem with people is problem people had was when they did the parallel. And is that showing up? It'd probably be better on the PC. So the thing that I think confused folks is if you look at this, you have these two pieces, and it seems fairly straightforward. But one thing that's a little bit surprising is look at the numerator of this part. It's 1/3 z inverse, and there are no constant terms. There's no +1. There's no anything. So what does that mean? That means that whole structure is going to look a little bit bizarre because there's going to be nothing there. And that's what's shown here. I just simply took out that line. In fact, I drew it to start with and then said, whoops, there's no B0 there. I better erase it. And some people just pushed ahead and put a 0 weight on that bar. And I gave them full credit for that. That's just letting the the template help you not make a mistake is what that's called. So either way is fine. I left it out, but you can put a bar in there, put a branch, and put a 0 weight on it if you like. That's the only problem people have. Most people didn't have too much problem with problem 2. So let's talk a little bit about problem 3 because it's so fundamental. And this is the type of problem that you're definitely going to see on the final, so won't be a surprise. So I'd like everybody to understand this problem and be ready to get all 30 points for it again next time, because this should be this hopefully is won't be a problem for you. So let's go through it. Let's see. All right, the key point is it says the discrete time system is required to convert the sampling rate of the signal from 16 to 8 kilohertz. So 16 kilohertz in, 8 kilohertz out. So what does that mean? What's happening? Well, 16 is larger than 8, right? So it's faster sample rate in, slower sample rate out. So in this case, it's going to be you're downsampling the signal. I hope that's clear. Part A says sketch the block diagram of a rate conversion system. Include the frequency response of any required filters. So this is the kind of stuff you could have put down on your sheet of paper if it's not totally memorable for you. And so if you're the only thing you'd have to really commit is understand when you're upsampling and when you're downsampling. So you're increasing the sample rate is upsampling, decreasing it is downsampling. So for part A, you can say, well, I know I'm going to be downsampling, and so what does a generic downsampling system look like? And I jumped too quickly to 2. Let's make that M, because that's typically what we put. We put downsample by M. And our filter was generically what? Pi over M minus pi over M, the gain of 1. And this was HE j omega. And so if you drew this diagram and said M equals 2, that's full credit. It's just how does the rate conversion system work generically? And this is something that you'd have to do. Now, whether you do it smart with polyphase or you do it some other fancy way, it doesn't matter. At the end of the day, you're going to have to filter it to keep it from being aliased, and then you can remove the samples. How smart you do it is another issue entirely. So that brings us to part B. Sketch the block diagram of a polyphase implementation of the system. Now there is a generic block diagram for the polyphase down conversion and the polyphase, or the polyphase down conversion, the polyphase downsample and then the polyphase upsample. So hopefully on your sheets of paper you have something, and I'm going to do it sort of generically as a reminder of what that should look like. And it goes on like this for some time until you get to m minus 1. And this is what? E of m minus 1 of z. Is this all fitting? Yes. So a bunch of dot dot dots here. Dot dot dot. And this connects. Connects. And there is y of n. And then there's the, basically it turns out to be the transpose of this for the upsample case. But for the downsample case, here's the generic thing you'd want to have on your sheet of paper before the final exam. So assuming that you had said picture on your piece of paper, you realize that since m equals 2, luckily this is not going to take all day to draw, right? We're just going to downsample by 2. We have E0 of z. We have one delay in the system. Another downsample by 2. And we're done. So that was basically the answer to part B. Sketch the polyphase implementation of the system. Now I kind of left out, okay, I say E0 of z and E1 of z, but what are those? And that's what gets us to part C, which is saying, okay, sketch the impulse response for each polyphase filter component if the overall filter has the impulse response given below. So if you had h of n of this, how do you get those e's? And I hope everyone could tie that back to what is h of n? Well, h of n is the impulse response of h ej omega, which is the one that's determined by having the cutoffs at pi over m, or pi over 2 in this case. So if someone went off and designed a filter that was causal and realizable and met some sort of specification, you'd end up with this h of n here for the purposes of our problem. So if you remember how that's another useful thing to put on your sheet is how to derive these. Because for our case, since I guess I can put the answer and then put the AEG and E1 of n, BDF, because these are basically the even and odd parts of that h of n function, right? Now, one thing I think people got confused on is some folks almost tried to rederive the entire polyphase approach kind of from scratch, which that's kind of tough to do in an exam setting, especially if you're fairly new to this stuff. And so one thing I think you have to remember is what we want to get out of this is have a regular old impulse response that we can implement through a difference equation, through FFTs, which we're going to talk about today, or however you want to do it. You just want it to be straightforward. And so these E1 of n and E0 of n are just regular looking impulse responses. There's no gaps in here. This is after we've taken out this, we've done the downsampling, and we have this z inverse, and so this isn't E1 z squared or E0 z squared. Some people had that in the is part of the mix. So that's the answer to part C. And I think we had, let's see, was there any other parts to this that was important? So make sure you get those on your sheets for the final exam, because you'll definitely have a problem like that. All right, I think the last thing we want to look at is problem 4. Yeah, maybe we'll look at 4 and 5. So let's take a look at 4. So most people got part A right, which is great, because that's pretty fundamental to the course. So for this one, you're given X of n, that's your input sequence you want to process, and H of n was the impulse response of the filter you want to implement. And that's one way to look at it, and so the linear convolution is what you want. That's the output. And we're going to calculate that impulse response using the method of y of n is the inverse DFT of the products of the two DFTs of the sequences. So what size DFT is required to avoid aliasing? And most people got that right because that is your standard L plus P minus 1. If there's a linked L sequence and a linked P sequence, if you convolve them, the output's L plus P minus 1. If you do this method here, what is the inverse? What does this process really do? It really does circular convolution, which will be equivalent to linear convolution if everything is the right sizes. Otherwise, it'll be aliased. So most people got that right. As what? We have how many here? If we count the numbers, this is indexed at 0, but I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 samples there. 1, 2, 3, 4 samples there. 9 plus 4 is 13, minus 1 is 12. So a 12-length DFT will suffice. Part B. If the linear convolution is given as below, what's the 10-point circular convolution? This problem, some people tried to attack it with a lot of brute force. But what I was hoping is that you've been given the linear convolution. And how many terms is that? Well, you know it has to be 12. And if you count them, starts with n and goes minus 1, 2, up to 11. So there's 11 terms plus 1 is 12. So I think I did this in MATLAB, so this might even be the right actual convolution. So what I wanted people to recognize here is I can get a circular convolution by aliasing linear convolution. Usually we're trying to avoid aliasing. This is the time I'm saying, well, what is the 10-point circular convolution? Well, since you have the linear, just alias the linear and be done with it. And so I was hoping that people could write down, okay, I'm just going to take these last two and alias them onto the first two and write that down so I understand what you're doing and then do it. And that would be a full credit answer. So the final output, let's go to the desk here, would be recognizing this is problem 4, part B. So what we're trying to recognize here is circular convolution. Circular convolution is linear convolution or I was going to say aliased. Maybe better to say circular convolution is aliased linear convolution. So the key is alias so that there are 10 output samples. And so that's kind of the key step. So if we look at our, let's just write down what we've got here. I said that X of n linearly convolved with H of n was 2 minus 6, 7 minus 5, 1, 5 minus 9, 9, 1, 5, minus 9, 9. Minus 8, 5 minus 2, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. So I believe that is right. But I want to get the 10-point circular convolution. So that means this minus 2 is going to be aliased, so there's only 10 outputs. So how do we do that? We have to pick these two up and move them over to here. They're going to alias back around because the sequence is only 10 length long. You can almost think of it as if we said that we're going to index this from 0 to 11, And now all of a sudden we're going to enter modulo 10 world. So anything that's greater than I guess 10 is going to get 10 subtracted from it. So these guys here are going to alias back here. So this -2 lands on 2, and the 1 lands on -6. So -2 plus 2 is going to be 0. 1 minus 6 is -5. And everything else is the same, ... all the way to 9 minus 8, 5. So we end up with 10 outputs. And that was kind of the way I was hoping the things that people would recognize, because obviously trying to do that 10-point linear convolution in the exam, I was hoping that people would think, okay, he doesn't mean that. That would be insane. But some of you gave it the good old the good old try. You just got in there and tried to do something with it. But yeah, I didn't want. We wanted to try to do it in an easy way that reflected your understanding of the concept. Let's go back to part C. So this problem is if h of k is the 5-point DFT of h of n, kind of a standard nomenclature here, right? H of k is the 5-point DFT of h of n. Sketch the 5-point DFT of h of k. So when you hear DFT of h of k, I hope you really thought, oh yeah, that's that duality stuff all over again. When you talk about DFTs of sequences that are already a DFT of something, and I think here we are, here's a perfect example of it. Property 4 says, and this is the way Oppenheim and Schaefer do it, and I tried to stick with that nomenclature. If you have a capital X, that means you're in the frequency domain, and you've taken a DFT or something. So now we've taken a DFT of some sequence x of n. This capital X of n means, okay, I've got the DFT of that, and he uses n here because we always want to use n as the index of the thing we're going to take a DFT of. And he's trying to be consistent in that way. So if we take the DFT of this, we end up with what? It's just a time-reversed modulo n version of x of n times cap n. So let's go back. To our choice here and say, well, given that we know, and let's put a new sheet, part C. So given that we know if we have a DFT of x of n, and we take the DFT of that, what do we get back? A shifted version, time reversed. And now I can't remember if he used n or k, but it's property 4. And we're time reversing x of n. Well, we know what x of n, let's see, now we're messing with h of n because it's a lot easier. We're using this as the property. So what we want to do is look at h of n. And so let's go back to the PC. The problem was about h of n, so that's good. So if we remember before, h of n is what? That's 2 minus 2. All right, 2 minus 2, 1 minus 1. So there's h of n. 1, 2, 3, 4, up 5. It's a 5-point DFT. So there's our sequence. And we want to implement this function on it. So the first thing we got to do is figure out how do we time reverse h of n. And the first way to do it is to, I think the easiest way is just to remember that, well, if you're going to do this time reversing business, what happens to the very first sample? It's the 0th, nothing changes. And then you basically take the rest of the samples and reverse it. And so it's 0, minus 1, 1, minus 2. And that's one way to do it, just by, I remember this is how it works. The other way, and we won't do all of it because don't want to totally get bogged down, is to use that table approach. Right, 0, minus 1, minus 2, minus 3, 0, 1, 2, 3, 4. So we need a 4 on our table. And then remember, when you do the modulo on this, modulo 5, we add 5 to everything that's negative. So that's what? 4, 3, 2, 1. And remembering that this is 0 with 4, 3, 2, 1, everything else reversed was the whole concept of being able to just write it down. Because if you can remember that, you're in good shape. Otherwise, you can just use the table to keep yourself out of trouble and say, well, what is h of n? Let me write it down again. That's 2, minus 2, 1, minus 1, 0. So that's going to be 2. 4 puts me at 0. 3 brings me to what? Minus 1. 2 is 1. And that's 1, which is minus 2. So either way, you can kind of work it through and end up with the time reversed version. And I think we had multiple people do it using both methods. So once we have h of n time reversed, we just multiply it times n, which is 5. So since n is 5, the DFT of h of k is what, times 5? That makes that 10 now. 0 times 5 is 0, minus 5, plus 5, and then finally minus 10. All right, the last thing I want to look at is problem 5, just because that was a good problem for remembering how to do chapter 4 stuff, which we definitely will have to know how to do for the final. Let's go back to the PC here. And I think one thing was definitely confusing for folks was the fact that this signal has multiple frequency components. And I think that kind of threw people for a loop. What do I mean by that? I mean, there's some low frequency stuff here that's under 100 hertz, and then there's some stuff out here in these side bands that's greater than 100 hertz. And this is the entire signal that we care about. So the fact that it's not contiguous shouldn't concern you. I think that threw some people kind of in the ditch when they saw this. But no, the signal doesn't have to be contiguous. It can have different sidebands and frequency components. I mean, each one of these frequency components could have different signals that you're trying to transmit, trying to communicate. So we just have to carry this along and see what happens. In fact, I think I had a version of this problem on exams from other years where I had the sample frequency be 400 hertz instead of 800 hertz. In which case, if you think about what happens in your mind's eye when you look at this, these little sidebands are going to get nestled in between the other copies. And so there's no aliasing even at 400 hertz. But everything is all connected. But I didn't want to get that fancy this time. I wanted to just stay with a regular 800 hertz signal. So let's start from scratch and see if we can go through it, because this is the kind of step-by-step process you need to be able to follow. So for problem 5, the first thing was, what is x, e, j, omega after you sample the signal at 800 hertz? Well, hopefully this part is not too mysterious here. This is what, 200, 300. And this is the signal F, and this is all in hertz. So this is our analog signal. We haven't done anything yet. But then we're going to sample this at 800 hertz with XEJ omega. But before we do that, you could start to yourself, well, let me just stay in the analog domain and just go through the stuff that we did in chapter 2, kind of as a security blanket, and get the sampled version of the signal. And so if we do that, this is what, 2 pi times 100, 2 pi times 200, 2 pi times 300. This is 1 over t, which equals 800. Right? We're sampling at 800 hertz, so there's going to be copies of this. And so let's think, where are those copies going to be? Well, that's 2 pi times 100. That's minus 2 pi times, let's go out, let's see, that's 100, 200, 300. If I pick this up and move it over here, offset it by 800, that's going to be what? Out here at 2 pi times 500. Dot, dot, dot. So we've got the copies. Luckily, nothing's landing on top of each other yet, so that's good. But how do we go from this to the discrete time signal? Well, we scale everything using our scaling of cap t, right? So that gets us to where we want to go in terms of XEJ omega. So scaling everything, that puts us at this is still 1 over t, which is 800. But now we multiply this, what, 2 pi times 100, so it's 200 over 800, which is what, pi over 4 minus pi over 4. I think, did I put that there? Yes. So 200 times 2 is, let's put that on the screen, that's 400 pi divided by 800. So that's pi over 2, right? And 3 pi over 800 is going to be 3 pi over 400, so that's 3 pi over 4. And I think you get the idea. You can fill it in. The next step is recalling the upsample identity, because the next part, let's go back to the PC, was okay, you got x VJ omega. Now we need part B is sketch the spectrum of XE, which is the expanded version, which is the spectrum of the signal after it becomes upsampled. So that's where we're going to inject a 0 after every other sample, which we did that through analysis in part, problem 1. Now we're going to sketch the spectrum again. So I guess requires you to go back to remembering some of our formulas. The expanded version is j omega L. In this case, L equals 2. So that means we scale this frequency axis so that now it kind of, in some way of thinking it gets there twice as fast now, right? So actually we don't have any room to put it there. Let's try a different tactic here. Put it like this. So now it's at pi over 4, we're sitting now at pi over 8 minus pi over 8. Instead of pi over 2 and 3 pi over 4, it's half that now. So pi over 2, half of that is pi over 4. Half of 3 pi over 4 is 3 pi over 8. And we're still sitting at everything at 800. And you can do the rest of the scaling. and this was X, E, V, J, omega. So another good thing to write down on your on your sheets for the final is make sure you have these type of formulas because they're critical. I think what's the other one? All right, if you're downsampling it, what were we calling? I can't remember now the downsampled nomenclature. Was it X, D, of E, J, omega? Remember that one? Hopefully I'm doing the right nomenclature for the problem. I think it was something like this, where you had the shifted copies that could overlap of the original spectrum. Right. So another key downsampling formula to keep in mind. And I guess the final part was, what's the appropriate low-pass filter that will provide image rejection in this case? And so of course you could put the standard one where you'd have what, pi over 2. I think some people got I don't know if they got confused, but I accepted multiple answers because since we just noticed that this thing starts to repeat after 3 pi over 8, also a filter at 3 pi over 8 would also work as well. So there are several answers to that one. All right, that I think finishes up everything on the exam. And the stuff that I covered today in class, I wanted to use class time for it because you're going to see something like it on the final again. Maybe not the exact same problem, maybe instead of decimation of time, decimation of frequency, or maybe instead of upsampling, downsampling, but it's going to be second, same song, second verse. So I want to make sure everyone has a chance because, well, if you learn it, that means I don't have to spend hours and hours trying to figure out how to grade it, right? When people do well on exams and understand the material, it's very easy to grade. It takes all your Thanksgiving vacation if nobody understands what you're talking about on the exam. So I'm hoping to help you, learn something and also help me because I learned my lesson. So let's, if you have any questions about this material, let me know, and I'll try to answer questions either over email or for office hours. So with that, let's finish up decimation and frequency and start getting into applications. So for the rest of the course, they're pretty much just going to do applications-oriented type stuff. Like, all right, you got a lot of tools now. You know how to do filtering. You can design filters. You know how to implement stuff. You know how to do DFTs. So what we're going to do is talk about some engineering choices and how you put things together, how you compare things, and even do a little bit of spectral estimation, I think, right before we quit. And if we have time, which we probably won't, we'll go into array processing, which is basically taking your frequency and time stuff, and now you have space and spatial frequency. So you can really start to sink your teeth into some of this stuff. So let's start getting forward. Now I think I just tried to copy what we did on paper into these slides. So we're going to kind of skip those up to decimation and frequency. I want to get to the final slide. That's right. The summary. So what was the difference? We had decimation and frequency, decimation and time. If you recall, last time we did some clever manipulations and all of a sudden, poof, decimation and frequency block diagram looked like decimation and time. So what's the big deal? Why bother? The key is going to be in how one of them has normal input and bit reversed output. One of them has bit reversed input and normal output. Which, if you don't think that through carefully, you think, aha, they both aren't any good. But they can be used together to actually kind of help. They both have the same number of complex operations. It's on the order of n log n, where n is the DFT length. So we've got two tools. They sort of have complementary I/O in some way. So let's see. We've got the two flow graphs, transposes of each other, and they both allow for in-place computations. I forgot about that, so they're very efficient in terms of memory. And the key difference is decimation frequency has normal input but bit reversed output. Decimation time has bit reversed input and normal output. So let's talk about how we can use them both. So I wanted to kind of create a very simple example so I could stick it all on one slide with everything, and at the same time sort of show how a real system might work, but at a much smaller scale. So let's think about a block convolution example and pretend we're going to do overlap save, but it doesn't matter. It could be overlap add, but we just need something to concentrate on. And so if you recall that algorithm, what'd you do? You had a DFT size that was fixed for whatever reason, and you fed in data. And if it was the very first record or frame, what'd you do? You put p-1 zeros in front of it and filled it in with regular data until you ended up with the DFT length. And then as you kept going, you had to overlap sections with data. And then after you did the operation, the filtering operation, you take out, or I guess you'd throw away the p-1 very first samples and take the rest of it. But the bottom line is you needed some DFT length. So let's kind of step through how we do this. We get data that comes in. This is the input data. So we're calling it x0 through x7. We're pretending we have, like, the quantum FFT processor of length 8. It's super fast. We love it, so we're going to use it. It's length 8, though. So what we do is we get the data in this buffer. It's ready to go. It's the data section we want to use. And then we do the DFT. Well, we're using decimation and frequency FFT. But when we do that, what happens? The data comes out in this bit reversed manner. So, okay, that may be an issue, but we're using that, and we're going to step through and see why it's actually a reasonable use of the decimation frequency for FFT. So what's the next part? Well, the next step is we have to multiply that times the filter response, right, after it's been DFT. So typically in a real application, if we know we're going to use length 8 DFTs, we're going to take our filter impulse response, DFT that, and hold it in memory somewhere, because we're not going to do that over and over again. This filter normally isn't changing. So normally you do that once, it'd be saved off in memory, and you'd use it on every data that comes in. So I'm thinking of it like a person who goes off, engineer designs the filter response, they do the FFT, they store that in RAM somewhere, or in memory on PowerUp. So we have that, but guess what? It's also stored, after we took the DFT and stored it in memory, it's also in bit reversed output. So when we multiply the bit reversed outputs together, they're in the right order. So this is good. So x of 0 times h0, x4 times h4, etc., etc. So we end up with this sequence y that's in bit reversed order. Well, that's great because we have a decimation in time FFT, inverse FFT on the shelf. So if we use the decimation in time version, it needs this bit reversed input, and then it squirts it out in normal output, which is good. So when you back away from the screen, you see what I got in was normal output, or normal input came in, normal output came out the back. So it's a reasonable system. You wouldn't want to have normal input in and some sort of out of order stuff in the back, because especially communication signals, the time order matters. It might be gibberish otherwise. So this is kind of a simple example of how this. How these algorithms can work together. So let's see. So I think the next thing I'd like to do is do kind of a bake-off, an engineering trade-off thing where we can look at a problem. We have a set of specs, and we talked about IIR filters. We talked about FIR filters. You can design them. You can use MATLAB. You can do it by hand if you have to. Why would you use one as opposed to another? Well, we know how to use difference equations to implement either one. You know that the FIR has guaranteed linear phase, which is nice. But let's just do a comparison and kind of go through the steps so you could actually do your own comparison for your own purposes. So for our example, let's suppose we have a filter. These are our requirements. We have a passband frequency of 0.5 pi. The cutoff frequency is 0.6 pi. So, pretty close, not a very wide transition, and it needs 60 dB of attenuation. So, hopefully right off the bat, you're thinking in your mind, okay, that's 0.5 pi, it's 0 dB, then all of a sudden that 0.6 pi goes down to minus 60 dB, And then, so that's a very narrow transition region. I expect a high order filter to be coming out of all this. So I wanted to compare this using a Hamming window and for our FIR entry into the sweepstakes, and then we'll use a Chebyshev Type 2 as our IIR example. So if you go into MATLAB and put in the specs and hit go, it spits out a ninth order filter for the Chebyshev. If you go through the Hamming window design process, and I'm sure that's FIR1 basically. So I think I just messed around with FIR1 until I got a order of the filter that met the requirement. It's 55th order filter. So 56 coefficients here and a ninth order here. So we have like 18 or 19 coefficients for this one and 55 for that one. So if you're going to implement this with a difference equation, right off the bat, you'd say, wow, why would I ever use an FIR filter? That's much, much more computations. So I just wanted to plot the frequency response of these two things just so you can kind of see. We're comparing apples to apples. Their frequency responses are very, very similar. The gain is what, minus 6 dB for the FIR, which is what FIR1 advertises when you read the fine print in the MATLAB script. The IIR was minus 3 dB, and the gain at 0.6 pi, basically 60 dB below that. And so they're pretty close to the same. And you can see the IIR has that ripple in the stop band that you're accustomed to seeing. Okay, so we've got our two filters. They know they meet our requirements. How are we going to implement this and compare it? So first off, let's look at the IIR filter. So we can go back to our difference equation template and say, okay, we know it's going to have this much stuff in it. And so the ninth order has 10 coefficients. I guess that's what, B0 through B1 through B9, and then A1 through A9. So you get what, 19 total? Yeah. So you end up with 10 A coefficients, 10 B coefficients, 19 total complex multiplies. I think A0 is 1, so it might save you 1. But you see it's on the order 19 complex multiplies per output sample. And that's one of the key things we have to remember is what is the number of ops per output sample, which at this point seems like a fairly banal observation. Well, of course, you put the inputs in, you get one output after you do these. But now we're going to think about it in a slightly different manner. Implement the FIR filter. And now here's a big suppose. This could be different depending on your situation. You know, if you had a different size FFT available. But suppose, just for the sake of a problem, we have a 512-point FFT engines available. So you have a very efficient 512-point FFT that you're going to use to do this. Well, the FIR filter has 56B coefficients, right? So we can go back to our recipe of how this works and say, well, that means P in our overlap save algorithm, or overlap add, is going to be 56. So, and data has overlapping samples of length P minus 1. And so if you do that, remember that's the overlapping samples per section, which turns out to be the data that you also ignore once you get it out of the FFT processing. So how many new samples do you put in? Well, it's the 512 minus the P minus 1, which is 457, which, like I kind of anticipated myself here, the P minus 1 are aliased, and so you get 457 out. Everything else is aliased and you throw away. So every time you do this FFT process, you get 457 output samples. And the FFT is the n log n. So you can kind of see, okay, we're going to have to do a little bit of accounting here to keep track of it. Because it's going to come down to, well, just how efficient is that FFT? If it's really efficient, well, you're going to divide it to get it down to output sample or multiplications per output sample. You know, you're going to have to divide it by 457, whatever that big number is. So let's do a kind of a simple example. See if this will get larger. So kind of back to the standard method. We're going to buffer the length of new data. Data comes in, X of n. We'll get 457 new data points. We're going to fill it up to 512. Why? Because we have the leftover, points that have to overlap in this overlap save algorithm. So we'll take the new data, FFT it to length 12, 512. Now we already have our 512 point FFT filter response stored off to the side because we've already designed this thing and it's in RAM. We don't have to do it, so that's for free. So what do we spend? 512 times log 2 at 512 in log n. Then we had to do the multiplies. Well, that's 512 more multiplies that are possibly complex because we had to multiply these two things times each other. So we got to account for that. And then finally we had the inverse FFT. So that's another n log n operation. So by the time you're done, let's tally it all up. The total complex multiplies are 2 n log n because that's the two, the forward and the back FFT and inverse FFT. But then you got the 512 point FFT for the stored off impulse response. So you add all that up, it's going to require you 9,728 complex multiplies, or at least something on the order of that. So it seems like a huge number, but you got 457 outputs, not one. So if you divide it out, you're getting about 21 complex multiplies per output sample. So not totally crazy or way off compared to what your ninth order IIR filter was. So let's kind of get the conclusions all together here. So for this 55th order, 21.3 complex operations. The ninth one had 19 complex operations. Of course, the FIR had the guaranteed stability in linear phase. Usually has greater flexibility for most applications. But the IR has slightly less complex operations per output sample. Of course, that could change depending on different things, right? We assumed, I guess we need to stop here and finish up on Wednesday. Almost done.
Professor,
Yes.
I'm a distance student, and the final time is the same as the machine learning, so I have to take the machine learning final at that time. So,
Well, let me find out because I think you're not the only one, right? Isn't there other people?
yeah. There are maybe
I
three
thought
or
David was in there too, and maybe other people. Yeah, let me I know what I need to do. I need to ask Douglas what he normally does in this situation because you can't. I don't know about